afternoon. This is CIVE 638, Sedimentation Engineering. And my name is Victor Ponce, Professor of Civil Engineering at San Diego State University, College of Engineering, Department of Civil Engineering. And this is class number 102, meaning 10th week, second lecture. We have 2 lectures per week. The subject today is more on the sediment transport formulas. So we are now, I got finished describing the CIVE method, but I'm going to reiterate a couple of things that I forgot to mention. And then we'll move on to Engelund-Hansen, the graph by Julian, which I have already shown. And Ackers and White was a very important method because it's purported to be very accurate. Then we move on to the calculation of both Engelund-Hansen and Ackers and White. And at the end, we will get into the D11, which is the paper on ultimate sediment concentration, which I believe is one of our findings too. Not quite, it's a long story, and I'll tell the story when I get there. So at this point, what we're gonna do is we're gonna go back a little bit to the CIVE method. The CIVE 1964 method. As I already mentioned to you, this is a very popular method because it is constrained. It doesn't go anywhere within the chart. You can't go, you can't go wrong with this method. The only thing that could happen is that you may not be able to match the diameters. So there will be some extrapolation if you are above 1 millimeter or below 0.1 millimeter. Because that's the method does it that way. It's discharge of sands because CIVE was primarily focused on sands. As a matter of fact, the entire CIVE methodology, as I understand it, was done in the Niobrara River in Nebraska, which is a tributary, I do believe, of the Missouri. So, but the important thing that I want to mention to you at this point is something extremely important. And what is it? It is this, that you can see the sediment transport formulas. Basically, it's a kind of a rating, and it's not a complete rating because usually a sediment rating curve has a discharge, water discharge in the abscissas and sediment discharge in the ordinates. So he doesn't have this water discharge in the abscissas because he didn't want to do it that way. But it is a well-known fact that discharge per unit of width varies with the velocity. So that's what he did. He made it to vary with the velocity. And of course, it mostly with the velocity, but it also varies a little bit with the depth because had it not varied with the depth, these charts in here would end up in the same level. But no, that's not quite correct. There's about between 0.1 feet, which is extremely small, to 100 feet, which is about as large as you're going to get here in the US. You get an order of magnitude, and 1 order of magnitude and a half, which is not uncommon in sediment transportation. But the point I want to focus in here is this, that these formulas look like they're power functions. And if you try to define these power functions, you will see that the exponent of the velocities in the lower range is high, and then in the upper range, it starts decreasing. This could be maybe 7. Well, 7 is a good number. 7, 6, 5, 3, 5, 4, 3, eventually gets to 3. This is not quite 3, but it very approximates 3. If we had to do a calculation of the slope of these curves, we will end up calculating 7, 6, 5, 4, and 3 around here. And they're all more or less like that. That kind of shows that relationships of sediment transport per unit of width against velocity are based on these graphs, which depict or replicate the variation of the exponent of the velocity from 3 to 7. 3, I already mentioned to you, happens to be a bottom. It's a floor. It cannot be less than 3, but it could be more than 3. As a matter of fact, that the Boy's equation considers it to be 4. Remember, we talked about that already. Okay, so that's a good thing. Now, another thing that is good that we're going to emphasize later on, probably today, is why are the formulas like this? Why are not they straight lines? Why do they have a tendency to go for the exponent to come down as the sediment transport increases? When the mean velocity increases, the sediment transport also increases. Okay, and the answer that we have found over the years, after a lot of research, is that sediment transport, there is an effect of the bed forms on the sediment transport. Basically, the idea is this, and we're going to prove it later on to you. The idea is that when you have plain bed, you have a lot of discharge, and the M decreases in here. And if not, if there's dunes, then we're here. So we're basically ripples, dunes, plain bed over here already, because it kind of is in accordance with the bed configuration, from which we conclude, after a whole lot of research and observation, that what is actually happening in the real world is that the bed forms are making sure that the transport is reduced. Because by the time you get to the higher transport, there's no bed forms and you can transport a whole lot. How is that? The theory or the idea is that the bed forms are impeding the transport. They are reducing the amount of transport. So if there were no bed forms out there, all these curves would be out here, and they would be coming down in here straight at about 3, at about an exponent 3. You see, but they don't do that. They always come down, and they come down strongly. Why strongly? Because this is a full logarithmic scale. So there's a lot of variability in here. It doesn't look like there is a lot of variability, but there is a lot of variability. So with those two comments, I say that the CIVE method is a very good method. It's not only well encased within a certain framework, but also has these truisms implicit in the methodology, from which we were able to find and write quite a few papers back in the late 80s and 90s on this particular subject. 80s and 90s, and we were published one in the year 2000. Okay, so that's what I was going to say about the CIVE method. As far as the mechanism of the CIVE method is a little bit intricate. It's got this formula in here, 1324, which I'm sure CIVE had to think a lot before he ended up with this formula. There's a whole lot of trial and error in here, I'm very sure, like Marcus. And he finally got this equation, but it's just on a calculator. You can put it in an Excel sheet. I actually don't think you can, because you have to put all these in the Excel sheet. That's going to be not impossible, but it's going to be a very difficult procedure. Now, I should tell you, as part of the story, Professor Ponce likes to tell stories, that back in the middle 70s, we were charged with doing the modified Einstein, and we did it. And then after that, the boss said, Ponce, I was working with another student, by the way. We're both working together. And he said, Ponce, why don't you guys, since you already done modified Einstein, why don't you do CIVE? I said to him, that's a piece of cake. Modified Einstein was really tough. It took us 2-3 months to do that work. But CIVE, I figured we could do it quite fast, because it was just a matter of using the piecewise linear and so forth. We already knew all that stuff. So we did a CIVE computer program. Not just CIVE, we did 5 computer programs. I don't remember the names, but I know it was modified Einstein and CIVE. I think we did Engelund-Hansen also, and Ackers and White. I'm not sure at this point. But the point is that, that we were able to do that. Many years later, I found out I was going to go to a conference in South America, and I found out that somebody had published a methodology to do calculations, a computer program to do CIVE. And they had dressed it up. By that time, had gone by, and they had dressed it up in some kind of an input-output format, like on the periphery of the program, wrap it up and make it nice so that the input-output is really nice and really friendly. So I said to myself, when I found that out, I said, hey, these guys have actually done an algorithm, a computer algorithm on the CIVE method. That's cool. And I didn't know at the time that anybody had done it. But then I researched the issue, and I got to reading the paper that these people had published, and I found out that one of the references to their work was the original 1975-76 work that I had done. So it didn't take me long to figure out that what they had done is they had taken my program and wrapped it up and wrote a paper on it. That's good to be well recognized and so forth, but that's the fact that is, it was like that. We may be among the very few that have actually produced algorithms, computational algorithms, to calculate both the modified Einstein as well as the Kolbe. Okay, so let me continue on here. And the next method, well, I already shown this, so I might as well just show it. As you can see, there's a whole bunch of equations in here. Meyer-Peter are there low because they're gravel formulas developed in Switzerland. And then you have the other formulas, the Dubois formula, we talked about that already. Engelund-Hansen, we're going to be talking about it briefly. We don't really cover the others because there's just too many. In my book, I think I covered 5 and there were 50 altogether. Some of them are not really well known, but you can see in there that whoever did this, and I'm not sure exactly who did this, this comes from the book by Julian, Professor Julian from Colorado State. But I am not sure that Julian originated this graph. I would have to go back to his book and see how he referenced it. But this is an important graph because it's the Colorado River at Taylor's Ferry, which is where the Colorado River is measured. It's kind of an important point on the Colorado River where they measure sediment. So this is a historic chart of the sediment transport on the Colorado River. And as you know very well, you can do the rating by using formulas, and all these formulas are, or rather all these lines are in effect ratings, sediment rating. And I told you earlier, a sediment rating curve is water discharge in the abscissas and sediment discharge in the ordinates. And that's exactly what this is, okay? And then they went ahead and plotted data points for the Colorado River at Taylor's Ferry, and they came in the middle of the pack, which is good, which kind of goes on to say that those methods that are close to the data are supposed to be better. That's the conclusion that we get. So you can see Ackers White and Engelund-Hansen out there distinctively kind of right in the middle of the data. While Chocolates is not, Chocolates is a very old formula, maybe more than 100 years old, turn of the century, 120 years old. There's Shields. Brownlee was a professor over at Caltech. I have not seen his data, but now I'm surprised that he's in here. He's a well-known gentleman in the field. He was a professor at Caltech, Brownlee. Einstein, Brown. To be honest with you, I have not tried or used all these equations. So I can't really tell you firsthand about their behavior. What I know is the Kolbe 64, the sediment modified Einstein, and the Ackers and White and Engelund-Hansen, which we had as part of our suite of models. As a matter of fact, when I was doing this work on sediment routing in Bolivia, 1989, 1990, we took 5 models to work out there. And those are the 5 models that I already mentioned to you. We figured we had to provide a variety of models. And as a matter of fact, as the story goes, one of the supervisors challenged me and said, "Why are you guys hung up on the Kolbe method?" And I said, well, but that's the only one that's really, really predictable and good behavior, numerical behavior. And he said, well, the Kolbe method was developed in the US. I said, yeah, that's right. And he says, well, what is its applicability to Bolivian rivers? We're looking at a Piraí River in eastern Bolivia. And I said, well, as far as I know, sand is sand, quartz sand. Same specific gravity and so forth, so it should apply. And he said, well, you got to do something about it. We're going to do some measurements. So we did some measurement. We waited for the flood to come because that particular river, you can't measure the sediment while it's not raining because it's kind of an ephemeral, almost ephemeral river, basically. It's a very low discharge during dry flows. So we waited for 6 months for the flows to come and we measured it. We did 3 measurements over a period of a month. And sure enough, the measurements came on top of the curves, particularly the Kolbe. And I'll show you that later on. So they were convinced that there was nothing wrong with the Kolbe. And we continue to say that as long as you're looking at quartz sands, quartz feldspar 2.65, the Kolbe should be applicable. And of course, as long as you're within the range of sizes, which we were. So it was fine. So that's so much I'm going to say at this point about the Kolbe method. So now what we need to do is to move ahead here, and we're going to be moving into the Engelund-Hansen. Where is it? Calculation of sediment discharge by the Engelund-Hansen. Okay, here we go. Engelund-Hansen, right. Over here. So this program was done by one of our students. I believe we had a student back in the year when we did this, 2012. There should be a date in here. Yeah, 2012, October 29. So that's exactly 10 years ago that this program was produced by one of our students. We checked that everything and so forth. It's a good program, the Engelund-Hansen. Now, the Engelund-Hansen is a very convoluted formula. And I'm not going to criticize or hail any of these formulas because they're all complex. They all look like they were invented by some Martian, okay? And they're all different, totally different. So how am I gonna do, the only method that I developed that I think is my own method is the one that you had already calculated, which is the modified lane. Because the modified lane, what we did in the case of the lane equation is that we made it a sediment transport equation because Lane had not done that. Lane had just said there's a relationship between the discharge, the slope, the sediment discharge, and the diameter. But we made it an equal, a relation. Therefore, meaning that we had developed by doing that a sediment transport formula. It remains for us to perhaps test that sediment transport formula against the least ferry data and find out where it plots in the Julian graph. That would be interesting, but that's a huge project. I'm not going to do it. But we did develop the lane relation because we felt that it was necessary that it be done because it was dimensionless, and anything that's dimensionless is good. So that's why we did it. That was done 3 or 4 years ago, by the way. Only 3 or 4 years ago. After we've been toying around with these formulas for more than 20 years. It finally occurred to us that we could do it. Okay, so this is the formula. And if we check in here the reference, SCS National Engineering Handbook, Section 3, Sedimentation, Chapter 4, Transmission of Sediment by Water. So we get in there, you get the PDF of the Chapter 4, Section 3, precisely on the transmission of sediment by water. So if you're interested in this, in the construction, or rather the structure of the Engelund-Hansen formula, you can find it here. Now, this is not the original source. If anybody wants to do good work, they have to go to the original source and find out whether the authors made mistakes or not. But typically, authors do make mistakes, by the way. Everybody make mistakes. Just that we obviously, when we find a mistake, we try to correct it. But in page 411, I think it's 411. Let me see. Look at this, figure 4.2. That you can recognize that figure. Sediment low classification, adapted from Cooper and Peterson. I put colors and I put it into my book, but it's the same. 1970. So we have Shockley's formula, Meyer-Peter formula, Haywood formula, Meyer-Peter formula, Einstein-Bedlow function, Engelund-Hansen procedure. And I looked at it yesterday. Where is it? Well, not here, because this is kind of odd. And to be honest, all these sediment manuals that the government puts together, they're all confusing. They don't know how to write clear. I have not written anything on the Engelund-Hansen. All we did was I charged the student with taking the formula from the references and putting it on the web, which we know how to do. We can take any formula and put it on the web. So we did that. So it is my understanding that this is correct and everything. So if you're interested in finding out how exactly Engelund-Hansen did it, it follows from this graph in here. However, I should say at this point, or I should add at this point that that these are the formulas. So let's take a look at the formulas. This is interesting, by the way. I've done this yesterday, only yesterday. Not that I didn't use or know the formula, but it's been several years, almost 10 years since we did this last time. And you know, people have a tendency to forget as time goes by. So we have SS over here. SS is the ratio between the weights, the densities. That's a standard method that appears even in the best formulas. Always show the ratio between the weights, the sediment weight and the water weight. Then we have in here a theta parameter, which is the depth, okay? The depth is the hydraulic depth, correct? The slope. So when you have depth and slope, you're already talking about here about shear. Tau equal gamma RS or gamma DS. And since in here we're going to be dealing with sediment discharge per unit of width, it's always D or R is the same because it's per unit of width. So R should be understood that this could be either R or D. S sub S minus 1 properly because there's buoyancy in the sediment, so you got to subtract 1, and then multiply by D50. Okay, and in here we kind of get into the mode of the initiation of movement. Can you see the formulas are kind of the same formulas for initiation of movement? Then we have this F over here, which is fascinating and very interesting because this really looks like Professor Ponce's F, but it is not. Let me tell you why. If you look at here, the fruit number over GD, so the fruit number is in the denominator over here. So if you put the fruit number in the denominator F is equal to S sub O, so you end up with a 2 in here. I don't have a 2 in my formula. So that means that his F is one half of mine. Whatever it is, his F is 1/2 of mine. Let's remind ourselves that mine is 1/8 of Darcy Weisbach. So this guy is working with an F that is 1/2 of Darcy Weisbach. So right there, you have 3 Fs. Darcy Weisbach's, this gentleman, and mine. Mine is the only one that doesn't have a number in there. Now, I have studied this extensively, and this issue of friction appears not just in civil engineering, hydraulics, it applies in fluid mechanics, it applies in chemistry, and so forth. Different fields utilize this equation in various forms. And I know for a fact that the Darcy Weisbach is not the most popular. Some people use 4 in there instead of 8, and they call it something else. They call it a drag formula and so on. It's got all kinds of different names. The one that doesn't have anything, it has just a 1, that's, I already told you, that's the Ponce equation. I gave it the name because nobody's using that. Why is it that the simplest equation is not being used? I do not know. What I know is that Professor Simons introduced me to this equation without telling me, because he was using C over G squared, which is directly related to the F. As a matter of fact, I believe the F is equal to G squared over C, or the reverse. I don't remember at this point, but there's a direct relationship between RF, which is 1/8 of the Darcy Weisbach, and the C over square root of G that Professor Simons used to use in all his works. So he's the one that introduced me to it. I actually never discussed with him the issue of why didn't he use F. Never discussed it. I just, at the time, I was kind of trying to keep a low profile and didn't want to cause a lot of waves, right? So I didn't say anything. I figured that some other time, some other opportunity. But we did insist that the F was the simplest way of doing it. And I'm really kind of surprised and rejoiced that Engelund-Hansen are actually doing the same thing, only half of it. Okay, then comes the Q sub S. And this is a formula that I don't, should I say, I'm not going to say I don't like it. Who might don't like the Engelund-Hansen formula if I haven't studied it? But it has a 0.1 in there that is kind of pulled out of the air, in my opinion. 1 over F is correct. The theta to the 5 over 2, that's his sedimentation properties. We have the gamma over there to give it the dimensions necessary. And the rest of the stuff is respectable or understandable that it should be that way. And finally, we get the Q, total Q equal the width times the Q sub S. So it's a good formula. So what I'm going to do now is to run it for you with the kind of simple data. Channel width, I'm going to put a 10 in here. Mean velocity, let's just say simple data that relates to practice. Mean diameter, say 1 millimeter in specific gravity. I don't have to put the specific gravity because it says leave blank to choose S sub S equal 2.68. So I'm going to do the calculation in 154 metric tons per day. So that's a good calculation, because if I use a 10 in here, or rather a width, and I would use metric, it would be 15. 15, correct. Okay, so that's the calculator for. So if you ever want to do this calculation, you can use the calculator, or else you can go back into the method and do it. Use these formulas that are here and do an Excel sheet and test it with my calculator. Because if they're different and you believe that you're right, then you give me a buzz. You say, Professor Ponce, I reproduce this thing with Excel and it doesn't work. It doesn't jive with your calculator. So either I'm wrong or you're wrong. So, but we have to settle that issue. Who is wrong? But because these things, calculators, it happens, you know. It hasn't happened to us too often. I think I can remember 2 or 3 instances in my 15-year career using, 17-year career using calculators that people have told me that I had made a mistake. And I promptly recognized that. Okay, so that is the Engelund-Hansen formula. I'm not going to go over here because I've already been there. Sediment transfer, a new approach and analysis. Ackers and White were working with, I believe, with the Wallingford lab. Don't take me 100% on that one, but they're British, well-recognized people, spend their lives doing this sort of thing. So they're very well, they were at the time very respected, 1973. But respected is up to a point, because in sedimentation, you know, things are fuzzy. They're so fuzzy that 20 years later, in 1993, they went ahead and corrected their method. They said they had the wherewithal to say, well, I'm sorry, we made a mistake, we're going to fix it. So the 1993 issue or version of the Ackers and White is the most recent version. And it changed the results. I don't know, we tested this. I don't remember the exact number, but the number 30% sticks to my mind, that the results were 30% off in the original calculation, which, by the way, I already told you many times, that's not that bad. If it were 100% off, I would start to raise an eyebrow. Just start. But 30% is not that bad. So they had the conscience, I guess you could say, to come back 20 years later and say, you know what, we thought about this for 20 years and we would like to correct it. And they corrected it. So that's the Ackers and White method. The Ackers and White method is extremely complicated. Ackers and White, here we go. It's extremely complicated. Look at those equations that are ridiculous. Look at those equations. The first one is for the diameter. The other one is for the shear, that is the friction. This one, I don't know exactly what it is, the D sub GR. My memory is not helping me at this point. Then you got to go back to the references, of course. Then there's an A factor, which kind of looks odd, okay? And then there's an F sub GR factor, and then M factor, and a GR factor, and that's it, and that's it. This looks complicated, but when you do a calculator or even an Excel sheet, it could be easy, by the way. You just have a little patience and put it all together, make sure everything works, make sure you do it by hand so that you don't mess up, because Excel is so prone to messing up that I don't want to talk about it because I like it is enemies, because people love Excel, correctly or incorrectly. But the fact of the matter is that Excel is prone to mistakes. Why? Because every cell in Excel can be driven independently. So if you have 100 cells, you've got 100 things to worry about. And so more or less something like that, not exactly. I have stories to tell you, but I'm not going to dwell into that because it's not necessary. Our calculations are not like that. Our calculations are global. So Excel is local and our calculations are global. So the chance for us making a mistake is 1 in 100. The chance for Excel making a mistake is 10 in 100 or 20 in 100. And I'm not saying that because I'm Professor Ponce. Several of our faculty had told me that. I had one faculty whose name I don't want to mention. And one day he says, I spent all summer checking the Excel sheets of the student that was graduating. That's what he said. Checking the Excel, all summer checking the Excel sheets of the student that was graduating, just to make sure that he had done it correctly. So I'm not the only one that says it or that feels about it that way. Interestingly, though, that's the method that everybody uses at this point. So we got to respect that. Respect, I guess you could say, the will of the people. So this is the Ackers and White formula. And over here, I'm going to do the same thing. Hydraulic depth, channel width, mean velocity, what did I say? 1, right? Bottom slope, we put 0, 0, 1. Suffice it to say that the bottom slope is controlling in here. Is really what controls. Mean diameter, temperature, in this case, temperature is needed because it enters into the computation. The specific gravity is not needed, okay? If you would recall, the previous calculation came out 15. This calculation is coming out 18. So lo and behold, I proclaim that these methods are exactly the same. because they differed only in 10%, not 10%, 20%, which is wholly within the range of accuracy in any sediment transport method. Good. So be it. We proved that this was correct.
Okay. Hi, Professor. I'm here.
Who?
Margot.
Oh, Margot. You just got in, Margot?
Maybe 15 minutes ago.
Oh, okay. Okay. Make a comment in here. Okay, so that's it. That's the Ackers-White formula. Purported to be one of the best formulas. And we have used it, by the way, because when we were doing this job in Bolivia back in the 89 and 90, I told you we were using the 5 methods. And we put the 5 methods in the computer program. That was an interesting experience for me. And the story is fascinating. I'm going to spend a half a minute telling you about it. Let's not forget that the computers that we have now are not the computers that we have in 1989, particularly in Bolivia. So I was in eastern Bolivia, the boonies, and they were running some 286s, IBM 286s, which were extremely slow for the stuff that we were doing. And it would take, I don't remember, but it would take like 30 minutes, an hour to run, or more than that even. And there was always a chance that there was going to be an electricity problem. The light was going to go off and so forth, and then all the calculation was going to go down the pit. So I could not run the HEC2 program that they were advocating, because I figured that I was never going to finish the job, because in the middle of the HEC2, it was going to take hours to run. The light was going to go off, and I would have to reset from the beginning. So I told the bosses, I said, no problem, I know HEC2, I can do a HEC2 that will run in 1/10 or 100 of the time. And so we did. So we spent a couple of weeks building up from scratch a HEC2. They would also do sediment routing, which amounted to HEC6, because HEC6 at the time was the HEC2 with sediment routing. Those programs don't exist anymore, because in the year 1998, that is 11 years later, no, 9 years later, they were superseded by HEC-RAS, where RAS stands for River Analysis System, which contains both HEC2 and HEC6 and 2D, and now it has water quality, and they're even getting into 3D now. So HEC-RAS is going to be the model, the only model to use, because it's got several branches. So anybody that is good with HEC-RAS is going to have a livelihood in our practice, because a lot of people are using HEC-RAS. So I urge you to get on top of it, not just the HEC-RAS. Get on top of it, the theory behind HEC-RAS, the unsteady flow, the water surface profiles, and all this other stuff. Because if you get in there and you don't know the hydraulics, you're not going to be able to do it. One gentleman about a couple, 3 years ago called me up, and he was from the University of San Diego. Well, I think it was a lady, as a matter of fact. From the University of San Diego, it was not an engineering, they don't have engineering department, so there was some kind of geography department. I don't recall, to be honest with you. It's been a while, and I don't remember everything that happens to me. But this lady said that she wanted to run HEC-RAS, but didn't know how to do it. And that I recommend, she says, well, either you do it or you recommend somebody that could do it. And so I did that. I wasn't going to do it. I don't get involved in those little things, in my opinion, you know. So I recommended one of our students, and he went ahead and did it. One of our students helped that lady, who is a professor over at University of San Diego. And they presumably finished. Yeah, he reported me that they did it. So as you can see, running HEC-RAS is not an easy matter, a simple matter. You have to have a very strong basis in hydraulics and hydrology, particularly hydraulics. If you don't have it, you won't do it, or else you'll do it wrongly. And that should not be the case. Okay. Not to say that just because this program is the Army Corps program, that it is correct. I have caught the Army Corps in errors many times. Sometimes they fixed it, sometimes they didn't fix it. I don't know. You know, suffice it to say that Army Corps and I have a good relationship, you know, a professional relationship. And sometimes I disagree with what they're doing. which is fine. People can disagree. But the point is that that they are in the business, if you could call it a business, of developing models for general use across the world. They're doing it for US, but since the models are entirely open, meaning open to use, they can be used by anybody that with a computer that can download, and they're free download. They don't charge anything. So they're basically, it's a federal government that is supported by our taxes, and they're basically serving the entire world. How and when or how does that happen? I do not know, but that's actually what's actually happening. They are supporting, in terms of development of hydraulic and hydrologic software, the world, the entire world. Other countries don't have that capability. There's 240 countries in the world, and many of them, I'd say 90% of them don't have the capability. There's a few that do, but they're counted with the hand, the fingers of my hand. Brazil has some, I'm sure England has some. I'm sure the major countries in Europe, Germany and Spain in particular, they have their own softwares, but other countries don't. I think in Brazil, in South America, the only country that's kind of independent and purports to use their own software developed in their universities is Brazil. The other countries just use HMS. Some people are experts in running HMS in those countries. They run it all the time. You have to also realize that in order to become an expert in something, you have to do something very often. And that is typically the case. Okay, so having said that, then I am going to move on to the next subject, which is this ultimate sediment concentration. Ultimate sediment concentration, calculation, Ackers and White. Okay, fine. This is a paper that I published in 1988, and it has a long and interesting story of, how did I say it? Let's just say story, okay? The paper is called Ultimate Sediment Concentration, as it is shown in there. So this is what we're gonna say in here. In engineering practice, the sediment rating curve is used, very much used. The sediment rating curve, as opposed to the water rating curve. The water rating curve is a plot of water versus stage, area or stage. Typically in practice, we use stage, the water level, the elevation, the stage elevation. That's water rating. But the sediment rating is, as I said, repeated earlier, sediment, water discharge in the abscissas and sediment discharge in the ordinates. A very well-known and very useful relationship. I have shown you the Colorado River Elise Ferries that was published in Professor Julian's book. Okay, used to relate sediment discharge to water discharge under steady equilibrium flow conditions. What does that mean? Yeah, if it's a single curve, it's steady equilibrium, because in practice there's loops in the stage discharge, because the loops are created by the bed forms. If there are some bed forms, there's going to be loops out there no matter what. But those loops are very complex. They depend on the geomorphology rather than the bed forms. And we profess to largely ignore what the stuff going in there. Not really ignore, it's just too complicated for any simple regular practitioner to get bothered with it. That's a fact. I had a student of mine back in the late 70s, early 80s, that got a PhD in this subject. He wanted to be able to calculate the sediment rating curve. And he did. But I can report to you that his findings were never used because they were too complicated. The KISS principle comes back to haunt us, right? You guys know the KISS principle really well. The simpler the method, the more useful it is. So the suspended bed material concentration is referred to as sediment concentration, and it specifically excludes wash loads. Technically, wash load should not be part of the problem. Although I already mentioned this, that in the modified Einstein procedure, the wash load is included in there because it comes with, the calculation is done by size fractions. And there are some size fractions that come in the category of wash load. So that's one exception. Among the 50 methods, there's only one, the sediment rather the modified Einstein that calculates the wash load. Other than that, we don't calculate the wash load. We presume that it's not there, and if it's not there, we're going to ignore it. How much is it? We don't know. We claim that it is hydrology, and that is correct, because it depends on the hydrology of the uplands, technically not controlled by the hydraulics. The control by the hydraulics would be in terms of the slope and the velocity and the friction. Those are what's controlling the hydraulics. But if you got silt and clay in there that are depending on the supply upstream, they're not controlled by the hydraulics. So the wash load is a big if in sediment computations. So in this paper, we take it out completely. We say it specifically excludes wash load. It specifically excludes wash load. And I'm going to say that at this point, because this paper has a bunch of stories, and I'm going to try to tell you most of the stories about this paper, okay? The first story is that I did not invent this chart over here. I'm going to, over here, how interesting, it's not colored. It must be that I didn't do it or what, whatever. But this is a typical sediment rating curve. In Pigeon Roost Creek, watershed 10, 1960. Exactly where it is, I don't know. I did not develop this graph. I copied it. Where did I copy it from? From Manual 54. Allow me to say this, the Bible of sedimentation of the times, 1975, Manual 54, sedimentation engineering. It was the first time that the word that gave rise to the name of this course came about, sedimentation engineering, okay? It was Vanoni, Professor Vanoni of Caltech, that somehow put it together, or he decided to call it that. There was a committee set up that he was heading, I'm sorry. And they spent several years, I don't know how many, 3-5 years, typically committee work does that. And they produced this huge volume, about 600 pages, 700 pages, which I have read extensively over the years, ever since it appeared, 1975. And Vanoni did that. He was a professor at Caltech, I said, and subsequently, of course, he retired and he passed away. In the year 2009 or 8, I think it was, how many years is that? 33 years afterwards, there was a second ed of the sedimentation engineering, and that has a story which I'm going to share with you because it's an interesting story. The second edition was in the making for about 5 to 7 years. And there was a gentleman whose name I don't remember or I don't want to mention that was put in charge. And he, for whatever reason, couldn't do it or wouldn't do it. And finally, the stuff landed on Professor, his name, from University of Illinois. University of Illinois, 2007, 2008. And he gathered the committee and finalized the work, finally, if I can say finally finalized. And they published it in the year 2008 or 2009. It was the second edition of the sedimentation engineering. Now, normally, when you put out a second edition, that pretty much gives a death to the first edition. Meaning nobody's going to get interested in the first edition because the second edition was supposed to be better and so on and so forth. Turned out that that was not the case. People still saw the second edition, and they still required the first edition. And now, based on so many requests, ASCE has decided that they're going to sell both of them at the same time, meaning you want the sedimentation engineering manual? We're going to sell you both for $200. That's more or less what it costs. Obviously, you can order each one of them, but technically that's what they want to do, sell you both, because they feel that both people want both. Why is it both? Because they complement each other. There are a few things that are kind of old and they're not in the new manual. Plus, the new manual is twice as thick. Somehow the second committee did not do, if I may allow to say this, did not do their job very well. You got to call, you got to refine, you got to select, and then at the end, get to something reasonable, which should be on the order of, in my opinion, an esteemed opinion, maybe 600, 700 pages at the most. Well, the second edition has about 1,100 to 100 pages. I have it here. I have both, as a matter of fact. But to be honest with you, I checked the first edition more than the second edition. Unfortunately, it was a big effort, big in terms of its size, but not in terms of its quality. So This figure in here comes from the first book, and it's not in the second book. I bet they thought that it was not that important, but it is a tremendously important work, particularly for the work that I did. Okay, so this is a sediment rating. What they said in there was that the sediment rating is going to have a tendency to achieve a constant concentration. Can you see that? Those lines 45-degree angle are constant concentration. There's 500, 1,000, 2,000, 5,000 ppm of concentration of sediment. That's very thick chocolate, because usually you don't, when the water has 300, it's kind of clear. A little bit brown, but not so much. But by the time it gets to 1,000, 1,500, certainly 5,000, it looks like chocolate. Okay, and you've seen that before. And when there's a flood, it always comes like that. Never mind that the chocolate is half wash load and half sediment load. That's a tough one to answer. How much sediment load is the coffee? I mean, chocolate, etc. That's a different story. But the point is that that these charts were developed by some gentleman out there that did research many years ago. Maybe this is dated 1960, and the report is 1975. So this must have been done in the 60s for sure, absolutely. And they picked up this stuff over here. They said this. They said, in no uncertain terms, that there was a tendency, a clear tendency, for the sediment rating curve to swerve in here and achieve a constant sediment concentration at high sediment. That was what they said. But interestingly enough, and I'm going to here insert some of my own experience and thinking. The book had about 8 chapters or 10 chapters, and this one was part of the 7th chapter, which had a lot to do with the agricultural part. And for some reason, it was not paid a whole lot of attention. The attention was given to chapters 1, 2, and 3, and 4. By the time they got to 5, people got tired, and they didn't get to 7. So this curve exists in the manual, but most people have not seen it. Not me. I saw it because I read the entire manual. Okay. When I saw it, I said to myself, well, there must be something in here. I also remember what Colby had said. Colby had said the same thing. The only thing that Colby did not say was that it was approaching a constant concentration. He said it was reducing, but not necessarily approaching. But in here, they said we're approaching a concentration. Then I looked at the equations for this thing, and I realized that what they were doing, they were basically saying what Colby did not say, that if you go up here, the exponent of the rating is going to be 3. And it's not going to go below 3 because you cannot. Mathematically, physically, mechanically, you cannot. And over here, the exponent of rating was going to be 7. So that agreed more or less, large extent, with Colby's findings. And since we respect the work of Colby because he did a lot of measurements for a number of years, I also said to myself, this is very respectable work because it kind of reproduces closely the findings of Colby. So we decided to write a paper. 1988, original version. It was this paper over here, ultimate sediment concentration. There's another story about this paper, but I'm not going to tell you. I'm going to reserve it for some other time. It does not have a happy ending, so let's leave it out. Okay, so typically sediment rating curves plotted in logarithmic scale have large slopes and low discharges and smaller slopes at high discharges as shown in figure 1, typically. Sufficiently high discharge, the slope of the sediment rating approaches asymptotically a value of unity, a constant sediment concentration. This constant sediment concentration with streams tend to reach at high discharges is herein referred to as the ultimate sediment concentration. So we gave it a name, it's the ultimate sediment concentration. Don't forget that we were excluding wash load. We're saying that in a world without wash load, which is hard to find, but let's just say that we're speculating that that could be the case. Then in a world without wash load, we're going to have this behavior that achieving for high discharges a constant sediment concentration. Okay, so then let's calculate the ultimate sediment concentration. The following power function is commonly used to provide a fit between measured water and sediment discharge, where the M has to be defined. So for m equal 1, the sediment concentration is independent of Q and equal to C, the coefficient. Okay. The value of M1 appears to be a minimum value approached by many streams at very high flood discharges. Reference 1, page 476. Which one is the reference 1? Well, let's take a look. Reference 1 is ASCE 1975 Sedimentation Engineering, the Vanoni Manual. Vanoni was an extremely well-respected person. He was a professor over at Caltech. So we don't have any reason to believe that he made a mistake in here. He supported everything that all his associates were doing. Of course, Vanoni was the editor of that book. He was not the writer. And as you guys know very well, the editor directs everything, but he doesn't really write. He's got the writers for each chapter. The stuff is so specialized that they want to do 15 chapters. They got to find 15 writers, a writer for each chapter, a writer or two writers. Okay, so CIVE has shown that high values of N prevail at low water discharges, while low values of N are typical of high water discharges. That has been shown by CIVE. Since N cannot realistically decrease below 3, okay, the value of N is shown in here is between 3 and 7. Since N cannot decrease below 3, why below 3? Because 3 is the exponent of tau V, and tau V is the stream power, and everybody agrees that the stream power is emulates the sediment transport. So you don't want to go below 3 for the M. I'm sorry, for the N. In this case, the bed configuration approaches upper regime, in which bottom friction is largely due to grain roughness. So here we introduce the concept that Einstein, and we're going to come back to this later on. Einstein said in 1950 that there were two types of friction, the grain friction and the form friction. And he separated them and was able to calculate them individually or independently of each other. And then, of course, one can surmise that if you don't have bed forms, you're not going to have form friction. It's all going to be grain friction. So there's going to be an up and down in the actual flow in nature in terms of the friction, depending on whether the bed forms are prevalent or not. And this is what Simons also said in his 1957 paper that we have briefly touched upon. Their work that they did at Colorado State in the 8-foot flume. So everything I'm saying here regarding the various authors, all the way from the late 50s to 70s and 80s and 90s, matches. Well, ours is 88. This paper is written in 1988. So with n equal 3, equation 3 is dimensionally homogeneous. How is it that Mother Nature could have made m equal 3 dimensionally homogeneous? Because the answer is because she likes it. Mother Nature likes dimensionless hydraulics. So there's a beauty in here on the numbers that we cannot forego. The 3 is important because it's dimensionless. 4 is not dimensionless. 5 is not dimensionless. You see what I'm saying in here? So the 3 is important. So because it's the 3 gives us an equation like this with rho in the front, where rho has to be there because that has to do with the gravity. The K is dimensionless, like in the case of what we talked about, lane relation, and the V is 3, and therefore everything jives, and K is a dimensionless parameter. We already briefly talked about this when we discussed the modified lane relation. The water discharge, we know that. In terms of the water, in terms of channel width, in terms of discharge per unit of channel width, equation 2 is recast as Q sub S over Q, which is the concentration. And the substitution of equations 4 and 5, this is just like straight algebra, leads to Froude number. So here we have the Froude number coming up as a big player in the determination of sediment transport. Look at this. Concentration of sediment in terms of the Froude number. So the Froude number is not just water, it's also sediment. Because of course, the Froude number is a situation of gravity and gravity and friction control the transport of sediment. So it's only obvious that this should be the case. Where gamma, we know the definition of gamma, and we know F is the Froude number, right? And I should mention at this point that the D of the Froude is the capital D. That's a theoretical definition of the Froude number. However, in practice, loosely, we talk about the D. Because the reason for that is because most calculations that we care to do are always per unit of channel width because the rivers are generally wide. So we're doing this per unit of channel width and then multiplying by the width of the channel, and bingo, that's it, we got the answer. So we've done, and that's very common type of calculation. So if it's per unit of channel width, it doesn't matter if the D in the denominator of the fruit number is capital D or lowercase d. In this case, we just kind of put it in there. But in practice, it should be uppercase D. Let me say this because it needs to be said. If you are doing a modeling job, where the modeling has to be very precise, because one thing is design and another thing is modeling. And there's room for all of them. Analysis, you know, engineering is separated into various fields. Modeling, analysis, then design, then construction, then maintenance, and so on and so forth, right? So the design, you can use D or D, doesn't matter, because the error is not going to matter. But in calculation, in modeling, numerical modeling, you have to be precise. And if you use lowercase d instead of uppercase d, you mess up, because you're going to mess up 2-3%, and it's going to be enough to throw off course the entire calculation. That's a fact derived from experience. We have a lot of experience running models. We've been running models for 40 years, and we know that that's in fact the case. And when a model doesn't run, it happens. It happens. You're confronted with two choices, and I'm deviating a little bit from the subject here, but let me just finish because that's important. You're confronted with two choices. Either you go back and find out exactly why is it that the model doesn't run. Like in this case, I'm using lowercase d, I should be using uppercase d, right? So you put the uppercase d in there in the model and so forth, and lo and behold, it runs beautifully because that was the problem. The other way you could do it, which is not the recommended way, is that you apply a diffuser. Because if it's not running, it could be that weakly unstable, and you can cut it out with diffusers, with mechanisms to introduce numerical diffusion, which can be done readily and in many ways, by the way, in models. You can weigh the stuff, you can do all sorts of stuff, and you can make the model run. Any model can be made to run, because if you put enough diffusion, it will run. The problem is that once you diffuse not only the signal, you diffuse not only the noise, but also the signal. The signal is what you're interested in. If you're diffusing the noise with the signal, then it's just a big noise and you don't know what the heck you're talking. And that's exactly what happens in many places, by the way, in many places. It used to be 30, 40 years ago where the topics that I am currently talking about to you were not known very well. You know, we have made progress in the last 40 years. So these things were totally unknown, and people were doing all sorts of stuff that were not really correct. Even the mighty Army Corps of Engineers was doing that. In their manuals, published manuals in the 80s and 90s, there were errors because of the fact that I'm just telling you right now, that if you want to run a model, you can make it run. You can put an aspirin in there. You know what the aspirin does, right? An aspirin diffuses the pain. So if you take one aspirin, the pain will be reduced to 10%, by 10%. If you take 3 aspirins, well, 70%. If you take 10 aspirins, you may kill the patient. It's exactly what actually happens in this case of introducing diffusers or elements that will produce numerical diffusion. Okay, that's a tough subject and one that I have covered extensively in my 632 class last semester. Not last semester, in the fall of the year, or the previous year. Okay, so alternate expression here, following expression relates to friction. We get the finally the equation number 10, which, as you know, is the infamous Ponce equation of friction, which, like I said, is nothing but a dimensionless Chezy equation. Chezy could have done it, but he was not hung up on dimensionless, which is I am. From the beginning, we were doing dimensionless work because we knew that that was the path to success. We finally get the F is equal to G over C squared. I already told you that Simons was using none other than C over square root of G, which is the square reciprocal of the F. So how is it that Simons was so close to the answer and didn't get there? I never asked the guy. He was my professor. I couldn't really come out and ask him that question for fear of something bad happening or something, right? People really think they're correct. Everybody thinks they're correct, right? But I don't think that in this case he was. Simons was a great gentleman, great professor, great mentor. He passed away in the year 2005, I believe, at the age of 87, 88 years old. He was the engine behind the success of the Colorado State University. Colorado State University as a center for global teaching of hydraulics and water-related engineering subjects. In the middle of the 70s, it was the largest by numbers. Graduator, no, it's not that. School that graduated the most PhDs and masters in hydraulics and hydrology and water resources. And I believe at the time I was there, it was about 40 or 50 PhDs every year, which is an amazing number. Most big schools graduate 5. We were graduating, Colorado State was graduating 30, 40, I don't know. It varied, of course, from year to year. But their peak was in the middle 50s. I'm sorry, middle 70s when I was there. Professor Ponce was at the peak, right at the peak, because since it has decreased, Simons was retired and many people retired, and it's not the same now that it used to be. They're trying to go back to they were 50 years ago, but I do not believe that has happened. But at any rate, so that's the story on how these formulas were put together. Okay, so so that is the summary and conclusions. Now we're going to get to the summary and conclusion. Typical sediment rating curves show a trend toward a constant suspended bed material. I had to clarify, suspended bed material. It's sufficiently high discharges. This maximum value of sediment concentration can properly be referred to as the ultimate sediment concentration. The ultimate sediment concentration is shown to be a function of a dimensionless bed material sediment transport parameter and a dimensionless flow parameter, the square of the Froude number, which is over here. Where is it? Yeah, well, yeah. No, it's not that. Well, it's a function of the slope, the F, RF, and the gamma, and the K. The K is the how can I say, the central non-dimensionless parameter that describes, quantifies the transport. Finally, summary and conclusions. Typical sediment rating curves show a trend toward a constant sediment concentration is sufficiently high discharges. I did not say that. It was said by Vanoni in his book. Actually, not Vanoni, there are people that wrote the chapter of Vanoni's book where this figure is put together, where it's thrown in there. It's put in there. So it's accepted. It's accepted. It has to be accepted. Okay, and I'm saying all that because it has not been widely accepted. Some people don't believe in this stuff. Okay, even though it's in Vanoni's book. This maximum value of sediment concentration can properly be referred to as the ultimate sediment concentration, repetitious there. The ultimate sediment concentration is shown to be a function of the dimensionless sediment transfer parameter and a dimensionless flow parameter, the square of the Froude number. Alternatively, the Froude number squared can be expressed as a ratio of bottom slope and dimensionless ratio of friction factor. I already talked about those equations because we already know that. Okay, applications. Equation 7 may be used for the calculation of suspended bed material concentration at high flow discharges. For instance, a sediment transfer formula applicable to high discharges is needed in the calculation of gradual earth dam breaches, right? Gradual earth dam breaches. That has been work that we have done over the years. It's been one of our projects to do calculation of gradual earth dam breaches. Whether postulated or hindcasted. Postulated is when you're saying, what if this happens? Let's figure out what's going to happen. Or hindcast, and hindcast means it has already happened. Now we're going to try to reproduce by calculation what actually happened. Do earth dams breaches? They breach? Yes, they do all the time. Here in the United States, elsewhere around the world. If they breach, why do we build them? Because we want the storage and we cannot afford, either we can't. Technically, we cannot build a concrete dam everywhere because the concrete dam requires very strong foundations, typically rock. You got to found concrete on rock. So if you don't have rock, you're not going to be able to do a concrete dam. Therefore, you do an earthen dam, which doesn't weigh as much. But the problem is that the failure, the catastrophic failure of a concrete dam is very rare, while the catastrophic failure of an earthen dam is very common. And interestingly, most of the dams out there, I would say 90% are earthen or more, 95%. That's just the nature of the beast. We've been putting these dams for at least 100 years now. Many of them have failed. There's an actual book that I put together with one of our students about several years ago, a collection of about 30 dam failures starting in the around 1900, so 120 years ago. How is it that they failed and why they failed? And the thing about the common denominator of all these failures is that it rains a whole lot, it overwhelmed the spillway, it broke through the breach, and it caused the breach. So then the question is at that point, and this is where we're headed to, is that how long is it going to take that breach to get for the dam to fail through the breach? And that's interesting because the shorter it does, the shorter time it takes, the worse is the flood. Because all that water behind the dam is going to have to come out in, say, 30 minutes. Interestingly, though, the dams that have been documented, and we actually have a paper on this, by the way, a documentation of time for the failure of dam breaches. And we have been proven through data, measurements and so forth, that is usually 2 to 3 hour breach, which is not good, but not bad either. It would be bad if it's only like 10 minutes, 15 minutes. Because you can see the hydrograph would have to squeeze and concentrate and the peak flow goes up, and therefore you got a major disaster. So, but nevertheless, we got to figure it out. The rate of breaching is important for many uses. Forecasting, security of, how can I say, what's the word for that? Making sure that a lot of people don't get killed or drowned by a flood, which, by the way, it does happen and it can kill people. So limited experience suggests the case normally restricted with a relatively narrow range. There's an example of the Bayonne Dam in Italy, which is an interesting example, by the way. It has nothing to do with earth dam breaches, but it has something to do with failures of dams. What actually happened out there at Vaillant, the spelling is V-A-I-O-N-T. For those of you that are interested in what I'm about to say and want to find out more about it, you know, nowadays with the web, you can go to the web, type Bayonne dam failure, and the web will show you everything there is to be shown. It is a very famous failure. What happened in Bayonne was the following. Italy, northern Italy, 1960, 1961, they built this huge arch dam. Now, we don't build any more arch dams. And the reason is because there are no sites that would take an arch dam. The arch dam is not like a gravity dam. The gravity dam is gonna fall or sustain on its own, gravity. The arch dam doesn't have any gravity, so it has to be against abutments that are very strong, like a hill, 2 hills, abutments that will hold the dam in place so that it doesn't go anywhere. So what actually happened in there was not that the dam went anywhere. The dam, I believe it is my understanding, it is still there. The problem was that the dam flooded this area, because all dams flood the area, right? And what happened was that the sides of the reservoir became wet and they became unstable. So it was a geological problem. The geologists should have seen this. As a matter of fact, they predicted that it was going to fall, but they said it was going to fall, take a while. It will take a while and it will be slow. A while, I don't know. I didn't read the reports, but you're assuming that it's not going to cause a lot of trouble. It will take a while to wet and to come down, but it is technically it could come down and it will take some time. That's what they said, the geologists. So the engineers went ahead and built a dam, an arch dam, Vaillant Dam, in northern Italy, I repeat, and then they filled it up. Well, I'm telling you that in the first filling, a few days, the entire hill on one side, I believe, if I remember correctly, came down completely, and it filled the reservoir that was already full. The reservoir was already full with water. It filled the reservoir, and once the material got into the reservoir, the water had to get out because the material was heavier. So it created this huge wave basically it's like you have a glass of water and you put your hand inside. If your hand can fit into the glass of water, and all the water is going to come out immediately, right? That's exactly what happened. Only it was not a hand, it was a half of a mountain that came down. So the dam's still there. It didn't fail. What failed was the wave that was created on top of the dam, which came down roaring, and it killed 2,000 people. There was a town downstream. The Italians never thought that this could happen. Had they thought that this could happen, they would have taken precaution, but they didn't. So that was one of the worst dam disasters in the world, I believe, in terms of people killed. 2,000 people were killed because there was a town downstream within a few miles. Read the story. It's a fascinating, interesting story of civil engineering. Okay, so now sediment rating curves are relatively scarce. Extrapolations are commonly made to encompass a range of high flood discharges, etc. I'm not going to finish in here. The sediment discharge extrapolated may result in a concentration exceeding 1,000 ppm. Right. I'm saying in here that if you extrapolate from the bottom, you end up with too high a sediment rating, which is impossible. You cannot get concentration exceeding 1,000,000 parts per million because that would be solid. Typically, the maximum concentrations that have been measured in sediment computations or sediment engineering are 200,000, which is almost wet concrete flowing down. You know, wet concrete can flow. Debris flows, like the ones that happen up here north of Pasadena, that's a place in the United States where debris flows recur almost every year because of the particular geomorphology, geology, and so forth, and vegetation, etc. So 200,000 is about the maximum. But if you do this calculation and extrapolation without paying attention to what we're saying in here, which all we're doing is regurgitating and repeating what was said in the Vanoni manual, then you'd have to consider that this thing is going to decrease. Later, next time we meet, which will be next Thursday, I'm going to tell you the secrets of why is this that way? Why is it that sediment concentration has to have an ultimate value? Okay, so with that then, and I'm also going to share with you an interesting story that happened to me because things happened to Professor Ponce regarding this subject, the subject of the sediment, the ultimate sediment concentration. But I think I ran out of time, so we're going to wait for next Thursday for me to tell you the whys and then the stories about this methodology that we developed in the year 1988. So that's 24 years ago. Okay, with that then, I am going to stop it. Thank you very much.